not because there is already resistance. Line, other drugs that may be useful but are not on the World Health Organization list. These drugs may be considered third-line drugs and are listed here either because they are not very effective, e.g. clarithromycin, or because their efficacy has not really been proven, like linezolide. Rifabutin is effective, but it's not included on the World Health Organization list because for most developing countries, it is impractically expensive. It's impractically expensive. So it's non-availability because of cost. Because as I have said, one of the problems with TB, if it was a one-off or a 1 week off, you can even sacrifice and buy the drug. But you can see you could be taking the drug for a whole 4 months. So it can be very, very expensive. So for the population, like the Kenyan population and the worst is, these are diseases that also hit mainly the disadvantaged. So they will be disadvantaged in terms of financial they have financial disadvantage. Therefore, if you give them an expensive drug, the adherence will be very, very, very poor. So you could have that as a third line, and we are saying the third line is we're very well explained, and we are saying it's if the effectiveness is not proven, the efficacy not proven, or very, 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 very expensive. But those are such drugs that in the Western world, the cost is not a major hindrance. So the antitubercular drugs are classified as, we have the standard drugs, we are saying for the first line, and you have the reserved drugs, and you look at the standard drugs, you have the bactericidal drugs, you have isonicotinic acid, which is isoniazid, INH, we have rifampicin, we have streptomycin, you have pyrazinamide. So all those are bactericidal, and indeed they are used for first line. Then you have the bacteriostatic, ethambutol, and diazepam. That cetazone is no longer used because on emergence of HIV and AIDS, there was total chaos. It caused a lot of toxicity. So for most of the countries, it has actually been withdrawn. But these are the drugs, you will find them in our clinics: isonicotinamide, INH, rifampicin, streptomycin, pyrazinamide, and ethambutol. Then we have said there is a reserved drugs, either they are very expensive, not very efficacious, and also have high toxicities. We are talking about capreomycin, kanamycin, fluoroquinolones, ethionamide, cycloserine, para-aminosalicylic acid. So these are the reserved drugs, and you will only go to them when you have resistance of the first line drugs or the basic drugs for the management of TB. So we're not saying they're not used. They are used because, as we have said, we do have a lot of multi-drug resistant TB where we must go for the reserved drugs. All we are saying is that you cannot start with a reserved drug. You will start with the standard drugs, and in case of resistance, then you move on to the second line. We can also classify them on basis of their chemical structure, just like always. And this is indeed our main area. And we have the salicylic acid derivative, like para-aminosalicylic acid. For sure, it is a salicylic acid derivative. You have the pyridine derivative, and we have isoniazid, which is also called isonicotinic acid hydrazine. We have the ethionamide and prothionamide. So all those are pyridine derivative, meaning they have that heterocyclic ring, which a 6-membered ring with a nitrogen, but aromatic 6-membered ring with a nitrogen, therefore pyridine derivatives. What, of course, they will have some structural differences, as we are going to see when you look at their structures. Then we have the pyrazine derivatives, where you have pyrazinamide. Pyrazine means that it is again a 6-membered ring, but it has 2 nitrogens opposite each other. We have in para positions. It has 2 nitrogen para to each other, and that is the pyrazine ring or pyrazinamide. Again, a first-line drug. We have ethylene diamino butanol derivatives, and ethylene diaminobutanol derivatives is where you have ethambutol. Again, we're going to look at it. We have the antibiotics, and as we have said, the antibiotics is again are still naturally occurring. We have streptomycin and aminoglycoside. We have rifampicin, rifamycin, and we have kanamycin or kanamycin, and kanamycin is also an aminoglycoside. So you have streptomycin, kanamycin, and even amikacin, which are all and this should be rifampicin and rifampicin, and the other derivatives are actually rifamycins. It is called rifampicin, and they are again naturally occurring, they occur naturally, and they are rifamycins. Then, as we have said, we have miscellaneous drugs which you can use. There is the fluoroquinolones, the ofloxacin, the ciprofloxacin, the norfloxacin. All those are the fluoroquinolones. Again, as we have said, they can go to the second or third line treatment. Then you have the macrolides, which we have said not highly effective, but where need to be, they can be added on in combination therapy to see whether we can improve on the effectiveness of the drugs. We have clarithromycin and we have azithromycin, and we have looked, fortunately, we have looked at macrolides. We did look at macrolides when we were looking at antibiotics, clarithromycin, azithromycin. So since we are not going to study them again, you do need to look at them. You do need to look at them because we have studied them, and now we are coming back to them. So it's important to read your macrolide so that you can remember the clarithromycin, the azithromycin. We will look at the fluoroquinolones and all the other drugs that are on this list. Some we will not look, the ones which are not currently in use, we will not bother going into details because we are not just studying for the sake of it. We are also looking at those drugs that are being the ones that are actively being used, not just any drug that can be used in the management of TB. We are interested in that which is currently being used. So we will start with our first drug, not unless if you have any question. Do you have any question? Don't have any question. We can start with our first drug, and our first drug is isoniazid, and isoniazid, also known as isonicotinyl hydrazine or isonicotinic acid hydrazine, which means even from the name you can see it has a hydrazine. It has a hydrazine. Hydrazine is when you have an NH2, that's what we call the hydrazine. So isonicotinyl hydrazine or isonicotinic acid hydrazine. And the structure, so the advantage is that it has a very simple structure. So that is the structure of isoniazid or INH. You can see, as we had said, it's a pyridine derivative. That's our pyridine ring. And then it has a hydrazine. It has a hydrazine where you have NH2, and therefore it's a very, 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 very simple structure. Isonicotinic acid hydrazine, because up to there is isonicotinic acid, and then you react them, the isonicotinic acid and the hydrazine, and you get isonicotinic acid hydrazide. Mechanism of action, we have already said that the Mycobacteria tuberculosis microorganism has a complex cell wall. It has mycolic acid, and indeed one of the drugs that goes for the mycolic acid, it blocks the synthesis of mycolic acid, is INH. And once it goes for the synthesis of mycolic acid, it has selective toxicity, although it will have some biotoxicity in the host, not a lot, because it's going for selective toxicity. It's going for a system or a pathway that is not found in the host, and hence selective toxicity. So it causes a decrease. It decreases or prevents synthesis of mycolic acid. Mycolic acid is a constituent, as we have said, of mycobacteria cell wall that is thought to be responsible for the acid fastness of the bacteria. I think now you can tell me these are things you have done. I might have forgotten. What is acid fastness? Can I get an answer? These are things that you did in microbiology. What is acid fastness? Lakini usiangalia kwa internet. Mko na tusimu twenu, ukiulizwa swali unaangalia mara moja. What is acid fastness? Hiyo wakati yote ninangojea, najua ni kukugoogle na Google. Don't Google. Remember, try to remember. Why are we calling it medical microbiology? So you did some medical microbiology in first year and second year. What is acid fastness? What is acid fastness? Hey, muko mumekimia, muko. Master Newton, naona umegoogle tu. I know you have googled. And that is the right thing. Its ability to resist decarborization by acids during staining procedures. That's what we call acid fastness. So we are saying the mycolic acid is suspected to be the one responsible for acid fastness. And najuanga that little time you just Google and you should be able to try and remember what you did. So we are saying it is responsible for the acid fastness of the bacteria, and it is a prodrug. So this isonicotinic acid is a prodrug, and it is activated in the body on the surface of the Mycobacteria tuberculosis. So actually the activation of this drug, it uses an enzyme that is found in the Mycobacteria. So the activation of this enzyme to the active moiety uses an enzyme found in the Mycobacteria. Sorry about that interruption. So we are saying that we have the mycolic acid, and the mycolic acid, we are blocking its synthesis. Once we block its synthesis, that means we will have interfered with the cell wall composition, and hence that will kill that microorganism. And the advantage, as I have already said, is that the enzyme that is responsible for activating the prodrug, isonicotinic acid or INH, is found within the Mycobacteria tuberculosis. So isoniazid is a prodrug that is activated on the surface of the Mycobacteria tuberculosis by cut enzyme to isonicotinic acid, or it can be activated to isonicotinic acid or the isonicotinic acid radical. And those are the ones that are active. Isonicotinic acid inhibits bacterial cell wall synthesis of mycoric acid, thereby making the Mycobacteria tuberculosis susceptible to reactive oxygen radicals. Isoniazid may be bacteriostatic or bactericidal in action, depending on the concentration of the drug attained at the site of infection and the susceptibility of the infecting organism. The drug is active against susceptible bacteria only during bacterial cell wall division, because for the mature microorganisms, the mycolic acid has already been formed. When you look at the mature microorganisms, their mycolic acid has already been formed, so you cannot disrupt the synthesis of the mycolic acid. But for during reproduction, when you are making new cells, that is when those new cells need to form the mycolic acid. So during that time, if you give that drug, it will inhibit the synthesis of the mycolic acid and therefore help in either suppressing these microorganisms of killing them. And do remember, we are giving these drugs in combination. This suppresses, this kills, or this suppresses, the other one suppresses, and therefore you suppress this microorganism to an extent that they cannot really be able to grow, because you are using different drugs and the different drugs have a different mode of action. So we are looking at that is our isoniazid. We have our it's activated by the peroxidase enzyme. It is activated by the peroxidase of the catalase enzyme, or the enzyme we are calling the CATG. And once it's activated, it gives us the activated form, which I either said it's a isonicotinic acid radical or the isonicotinic acid. And once it's activated, it actually binds. First, it binds the NAD or NADPH. And once it binds the NADP or NAD, then it binds the enzyme that is responsible for transferring the necessary precursor for synthesis of the mycolic acid. So once this drug or the activated moiety binds NAD, it binds that enzyme and inhibits it. Once it inhibits it, that means it cannot bind, or it binds the enzyme, it binds it in place of the precursor that you require. And once it binds it in place of the precursor that you require for the synthesis of mycolic acid, you will inhibit the synthesis of mycolic acid and suppression of that microorganism. So you have information of covalent complex with ACPM. If you look at ACPM, it's an acyl carrier protein. An acyl carrier protein is an enzyme. Acyl carrier protein is enzyme, and it inhibits acyl carrier protein and also the beta keto acyl carrier protein synthesis. So these two are enzymes. It inhibits both enzymes. And these two enzymes, all we need to know is that they are needed for the synthesis of mycolic acid. So once it blocks them, then you will not have synthesis of mycolic acid and hence death of the microorganism. Yes? Buyer, your buyer. All right. So we can put it in words. So you have the peroxidative activation, the peroxidase, all what we are calling the catalase enzyme, activation of isoniazid by the mycobacterial enzyme CATG generates isonicotinic acid anion or radical. It can either give the anion or the radical. If it is giving the anion, it is just this. I think I thought I showed. I will show it just now. If it's giving, so here we have our isoniazid or INH. So it is being acted by the catalase peroxidase, or what we are calling the CATG enzyme. And when that, you can see, you can form the isonicotin. You can either form the isonicotin aldehyde, and this isonicotin aldehyde can lose this hydrogen. If it loses that hydrogen, then this will be a radical. Remember, a radical is that compound that has an extra. Or it can give us the isonicotinic acid. If it gives us the isonicotinic acid, this is an acid which can undergo ionization. So when it undergoes an ionization, it will lose that hydrogen and you will have the anion. So loss of that hydrogen, because this is an acid, gives us the the isonicotinic acid anion. If this hydrogen is lost, then you can get the radical, and either the radical, and in fact I drawn the radical here, the C double bond O, and then radicals usually have a dot. So that is our radical. So either this radical or the anion can attach themselves to the NAD, because the NAD is positive. NAD positive, and this will be negative, and this will be deficient of electrons, so it can go for those centers. So we have this as an ion attacking the NAD plus or the NADP plus, because this reaction, that reaction of formation of the mycolic acid requires NAD or NADP plus as cofactors. Requires them as cofactors, and therefore they bind the enzyme. They bind the radical first or the anion first, and then that they bind the respective enzyme. And you can see, because it says on nicotinic acid, which is now binding the enzyme, it is not the proper precursor. It blocks that enzyme, just like we did. We were looking at when we were looking at the penicillins. We would say the drug binds the enzyme, and once the drug binds the enzyme in place of the proper precursor, then the enzyme is inhibited. So that's the same case we are saying here, that the activated, so the mycobacterial enzyme CATG generates isonicotinic acid, anion or radical that forms adduct, just addition. It binds with NAD plus or NADP plus, and once it binds that, then now it goes for the enzyme. This complex will then bind tightly to the ketoenol reductase known as INHA, which is the enzyme now which we require to convert to form mycolic acid and prevent access of the natural enol acid carrier protein substrate. So it binds the enzyme, and instead of the proper substrate which is needed for the synthesis of the mycoric acid, it binds there, inhibits that enzyme. That enzyme cannot pick up the proper precursor, and hence the mycoric acid is not synthesized. This mechanism inhibits the synthesis of mycoric acid in the mycobacterial cell wall. The INHA, the enol acid carrier protein reductase from Mycobacterium tuberculosis, is one of the key enzymes involved in this type 2 fatty acid biosynthesis pathway of the Mycobacteria tuberculosis. So we are only saying that this enzyme is very, very important. It's a very important enzyme in the synthesis of mycolic acid. So because remember, mycolic acid has fatty acids. So we are saying it's an important enzyme in the type 2 fatty acid biosynthesis. Remember, indeed, mycolic acid itself is made of fatty acids. So once you cannot synthesize mycolic acid, then for sure you will disrupt your cell wall. And once you disrupt your cell wall, then the microorganism will be suppressed or it will die, depending on the susceptibility of the microorganism. So we are saying isoniazid specifically inhibits long-chain fatty acid synthesis. So the long-chain fatty acid synthesis, they are necessary for the synthesis of mycolic acid. So inhibit specifically the long chain fatty acid synthesis, that is more than 26 carbon atom lipids having a short arm 24 carbon atoms and a long arm of 50 to 60 carbon atoms. This is what we are calling the mycolic acid. The mycolic acid has 2 arms. The short one is the alpha, which usually has between 20 to 24, and the long one is the beta, which has 50 to 60. And these are the ones we are calling the long chain fatty acids, whereby it has 2 chains. Remember the way I showed you the structure of the mycolic acid. It has the alpha chain and it has the beta chain. And all we are saying is that it will inhibit the synthesis of those fatty acids, which is the mycolic acid. And once it inhibits that, then of course it is obvious that microorganism will be negatively affected. It has been proposed that the INH is activated to an electrophilic species that accelerates the 4 positions of the NAD, the acylation of unsaturated fatty acids, which are essential for the synthesis of the mycolic acid. So this we have already said. We are saying that these species that you get, electrophilic is a center that is going for electrons. It is an electron deficient species. So it can, and the electrophilic one will be like the radical. The radical one is the one which will be electrophilic. It is deficient for electrons. It will be looking for electrons. And once you get that electrophilic species, then it will go for the electron-rich places. And once it goes for the electron-rich places, it will bind, form a complex, and that complex is not allowing for the formation of the mycolic acid. And hence, of course, once you don't form the mycolic acid, then as we have already correctly put, then the microorganism will have a lot of problems. And either, as we have said, it will either be suppressed or it will die, depending on the dose. Yeah, just disappeared. I don't know why. Thank you. The SARs, very important. We must always look at how does this structure of isoniazid affect or influence the activity of this drug. And SAR of isoniazid, nitrogen 1, you can see this is what we're calling the nitrogen 1, and this is what we're calling the nitrogen 2. And one of the things you see, the nitrogen 1, the N1, sorry, the N1 nitrogen in hydrazine side chain should be unsubstituted. And you can see this one, you cannot replace that hydrogen with any other group, even a methyl group, you will lose activity. So that nitrogen 1, N1 should remain unsubstituted. It can only carry a hydrogen. The N2 nitrogen can be substituted with an alkyl group or with groups to get active compounds. So we are saying this, that's why you have put R1, R2, and indeed the second nitrogen can be substituted with retention of activity, and we do have the drug iproniazid, whereby there was substitution and activity was still retained. Then we have replacement of the pyridine nucleus with other aromatic rings, such as benzene or piperidine or thiazolene, diminished the antitubercular activity. This pyridine ring, so we are saying the pyridine ring is necessary for optimum, not necessary for activity, because you can see we are saying it's diminished. You couldn't change that ring, the pyridine nucleus. You cannot change it with other rings like the benzene ring, or other rings like piperidine ring or thiazole ring. There will be decrease in activity. So for this kind of structure, the pyridine ring was necessary for optimal activity. Numerous derivatives have been developed. None of them have exhibited activity superior to that of the parent drug. And that is why it is isoniazid you find in the market, because isoniazid was found where even these R1 and R2 are actually hydrogens. It was isoniazid which up to today has been found to have maximum, optimum, and best activity in terms of toxicity. Other changes could have been done, and they were done, but the resultant molecules which were found did not have any advantage over isoniazid, why it is still isoniazid which has the best activity. When isopropyl group is substituted at R2, so whereby at R2 you put a CH, CH3, CH3. So R2 or R1, whichever, you put the group CH, CH3, CH3. That's what we call an isopropyl. So on this nitrogen, you bring in a CH, CH3, CH3. Isopropyl derivative named iproniazid was discovered. This drug, apart from antitubercular activity, it was also found to exhibit psychomotor stimulants. What happened is that when this, they try to do, as we have always discussed, structure modification is done slowly. And once you change the structure, you actually do clinical trials, and you move on slowly until now. You first of all, of course, do non-clinical trials, and then you move on up to clinical trials. And it was found out that when that drug was iproniazid, it was given to TB patients. They were also excited. Those, of course, TB being a chronic disease, people be depressed, and of course the cost and everything else, and of course you have to take your drugs, so it's a depressing disease. So it was found that when they were given iproniazid, their moods changed. So the iproniazid was investigated, and indeed iproniazid was found to also be an antidepressant. So that's what we are saying. It exhibits psychomotor stimulant activity. So you can see again, it has no advantage over INH, because again, you do not want to give a drug that has other CNS effects, and that is why the best drug in this class, or this class of the pyridine derivatives, is actually isoniazid. Yes, you can change these groups, but there was no added advantage, and that is why isoniazid is still the best drug for management of TB, the best drug in this class of the pyridine derivatives, because any other drug that was discovered fell short